Welcome back, Physics 30. This is the second part of Newton's Law of Motion. It pertains to pages 126 to 130 of your book. And in this section, we'll be looking at defining and providing examples of inertia, state that mass is a measure of inertia, provide examples, illustrations, or applications of Newton's laws of motion, and suggest practical examples which illustrate the need for a thorough understanding of Newton's laws of motion. So first of all, it was mentioned inertia. Inertia is an object's resistance to a change in motion. So objects want to tend to keep doing what they're doing. If there's a change or if there's a difference in movement, that resistance to a change is referred to as inertia. So for example, riding a bus, describe what happens if you're standing still and the bus all of a sudden accelerates. So if you're at rest, you want to stay at rest, so you want to resist moving. So your body wants to stay still while the bus moves forward. So it appears that you're moving backwards even though you're staying in the same spot on the bus. So for someone on the sidewalk, they would see you try to maintain a spot directly above the road where you were, and the bus is moving away from you. Someone on the bus, however, would see you moving backwards since they're moving along with the bus. So that is referred to as inertia of rest. If you're at rest, you want to stay at rest. And there's tons of examples of this. For example, if you have a playing card on your tip of your finger and if you put a coin on top, you could flick the card out from underneath the coin and the coin would stay on your finger. Or the old silk tablecloth trick, having a silk tablecloth with plates on top of the table. If you were quick enough, you could pull the tablecloth out, and the dinnerware, etc., has inertia of rest, so it would stay on the table. Another example here, this one's from the duotang. So you have a ball hanging from a string and a string below. If you have a quick pull, the smaller string snaps, but if a slower pull will break that string A. On here again, I talked about the tablecloth. So if you use a silk tablecloth, etc., you minimize the friction there, so hopefully you would be able to pull the tablecloth off. Just don't do it at Thanksgiving when there's a table full of food. Use an example of a riding bus again. Describe what occurs if you were standing in a bus that's moving, then all of a sudden it stops. So you are moving and your body wants to continue moving. If the bus comes to a stop, you continue to move. So it looks like you're flying forward on the bus, where actually, if a guy is standing on the sidewalk, just simply sees you moving forward at the rate you're moving, but the bus is stopped. So again, the two different observers on the bus or on the street would see two different things, but really it's the same motion. So that is referred to as inertia of motion. Now Galileo tried an experiment dealing with this. So I like to think of Hot Wheel tracks, because everyone has had Hot Wheels tracks likely at one time in their life. Those tracks minimize friction between the car and the track. So of course, if you had an incline here and an incline here, if you had a ball or a Hot Wheel car, it tries to achieve its original height as indicated by this dotted line. And of course, it doesn't, because there is friction even on a Hot Wheels track or a ball on an almost frictionless track. But if we assume it tries to reach its original height, and if all of a sudden I didn't have this incline, it was a flat surface, if we release a ball, the ball would continue on forever trying to reach its initial height if there was no friction. So rolling ball wants to achieve its original height. If it was flat, however, over here, the ball wants to move on forever trying to achieve that original height. But of course, in everyday life, that ball, even a Hot Wheels, if I had a track that extended the length of the hallway, the car would eventually come to a stop, because there is friction there between the wheels and the track. Also, some energy is lost in terms of sound. You can hear the car going down, etc. So friction and outside forces. Describe how inertia plays a role in an icy curve on a highway. So for example, that friction has a hard time being maintained if you're turning around a corner here. So this is kind of a bird's eye view of a car on an icy highway. So the car is moving straight, wants to continue to move straight unless an outside force forces it to turn. And if it's icy, that friction between the tires and the road surface has a hard time being set up, so the car continues to go straight. So the ice helps resist that change in motion. So friction, we mentioned that. It's any force that opposes motion. And if we take a look here, I like to refer to it like this. So we have our overall net force, the resulting force, is equal to the applied forces, and this symbol here is the Greek symbol sigma, which means sum of. So adding up all the applied forces and plus friction, you get the overall force that occurs. Okay, and we have a few different types of friction, and we have a kind of a mini unit after we're done Unit 1 on friction, so we'll just kind of touch on it now. So sliding friction depends upon surfaces rubbing against each other, and as mentioned here, when I get all my applied forces, friction is working in opposition to that. So if I use a positive sign for all my applied forces, the friction force automatically has a negative sign. Okay, and there's quite a few examples in the duotang dealing with this that you could look at. I'm going to go through one or two examples here. So the first one, a girl pulls a wagon with the force of 75 newtons at an angle of 30 degrees to the horizontal. The wagon accelerates forward. So if it's accelerating forward, that must mean there's a net force going forward. So draw a free body diagram. So here you have the girl here, you know it's a girl by the lipstick and the funky hairdo, pulling it up at an angle of 30 degrees to the horizontal. Okay, so that's this 75 corresponds to that angle force. So a free body diagram here, just drawing all the forces involved. So we have the force of gravity, we're pulling in this direction. Now that direction we're pulling can be broken down into a horizontal and vertical component, and it's this horizontal component that we're going to want to find because it is what is actually causing the wagon to move to the right. So, and we have force of gravity pulling it downwards. We have something referred to as the normal force, which is the force that the road exerts on the wagon, and as you know, see here, it's smaller than Fg, even though previously I said it is equal, but don't forget we're pulling it up at an angle, so Fn combined with Fy is equal and opposite to Fg, as I mentioned here. And I put this negative here because Fg is pulling downwards, so we think of that as a negative force. So if you take a negative of a negative, we get a positive, and this mathematical statement becomes correct. Fn and Fy is equal and opposite to Fg when you take the negative of Fg. And since this thing is accelerating, that must mean we have a net force going to the right, so our Fx must be bigger than Ff. And again, I put a negative there because friction is negative if Fx is positive, so to make it mathematically right, I put a negative in front of that one, so then all negatives become positive. Okay, so that's the scenario. Now, instead of normal force, just change this to upward force. Determine what the upward force F of y must be. So, of course, that is the opposite side. Opposite of 30, hypotenuse is 75, so you can see we have good old trig here again. Sine of 30 equals Fy over 75, so we get 43.0 newtons up. Determine what the net force must be if the friction is 10 newtons. So we think of that as being a negative 10. If Fx is a positive direction, Ff will be the negative direction. So of course Fx is the adjacent side, so I need to use cosine. So cos is equal to Fa over 75, and really we're figuring out Fx there. So whether you call it Fa or Fx, it doesn't matter. So that works out to be 65 newtons forward. But of course we have that friction working against us, so all of my applied forces combined with the friction force, and always remember friction is opposite to Fa. So if Fa is a positive 65, friction is a negative 10. So that works out to be 55 0.0 newtons forward. Okay? Lastly, definition here, I think we just have one here, inertia. So an object's resistance to a change in motion. So for example, if you're riding a skateboard, you and the skateboard are moving forwards. If your skateboard comes to a sudden stop there, you continue to move forward because you have what is referred to as inertia of motion. Okay, so there we have it. So this whole booklet dealt with inertia, looking at friction, looking at figuring out F net when we have friction and an applied force. Okay, we'll see you again.